In previous videos, I discussed the wave properties of EM radiation, including interference of waves, and the concept of intensity being related to the amount of undulation of the electric field strength at any point in an EM field. I mentioned diffraction only in passing, but since the concept of diffraction is key to understanding Abbe's theory of image formation in the light microscope, I'll discuss it in more detail here, using the Huygens-Miller mathematical model to simulate wave optics in a computer. At the end, I'll show how wave theory can be used to model the focusing of light by a lens, and compare this to models made using ray theory. Diffraction is an observed phenomenon of waves, whereby the waves traveling in a single medium appear to spread out into the region of shadow after they pass through an aperture of some kind. Furthermore, the illumination in this shadow region appears to break up into fringes of varying intensity. Diffraction effects were recognized at least as early as the 15th century by Leonardo da Vinci, and later described in more detail by the Italian priest and physicist Francesco Maria Grimaldi, who noted the fringes and who coined the Latin term diffractio to describe this effect and distinguish it from other ways light can be diverted, namely reflection and refraction. The term diffractio, or diffraction as we say in English, comes from the Latin diffringere, meaning to break into pieces, because the beam of light that should be confined by a crisp clean-edged boundary from the shadow, according to simple ray theory, actually breaks through this shadow barrier and appears to fragment into interference fringes, which are the pieces. Diffraction is a noteworthy effect because in the past, and heavily influenced by Isaac Newton, people thought light travelled in straight-line rays in a homogeneous medium, as if being composed of weightless bullets fired from a gun. These bullets were called corpuscles, which is Latin for little bodies, and so this is called the corpuscular theory of light. At this point, I want to take a little detour to explain something about the word photon. In the olden days, experimental phenomena, such as Einstein's Nobel Prize-winning photoelectric effect and Compton's scattering, caused some confusion, because, before the advent of quantum field theory, people couldn't imagine a way to explain those observations using the concept of light as a wave phenomenon. So, to explain these things, the old Newtonian corpuscular model of light was resurrected, in a revised form, in the 1900s. And this led to the dogma of wave-particle duality, with the concept of a particle still being conceived as some spatially localized object that travels through space in a continuous trajectory, and can bump into other objects, so exchanging momentum with them, as in classical physics mechanics. The popular notion, which is still prevalent to this day, of a photon being such a little billiard ball of light energy, which somehow, don't ask how, also has wave-like properties, comes from that era. However, nowadays we can explain all those billiard ball type effects as localized energy exchange events between quantum wave fields, and there is no longer a need for those old-fashioned ideas of light being made up of little billiard ball photons. The modern concept of a photon is simply a unit of energy, like the joule. But unlike the joule, the absolute amount of energy expressed by one photon depends on the wavelength of the photonic field, as per Planck's relation. The photon is the indivisible minimum unit of energy exchange into or out of a photonic quantum wave field. This model can explain Einstein and Compton, and there is no need to cling to old-fashioned ballistic corpuscular models of light anymore. Now, returning to Newton's original corpuscular theory. Such a theory could only be used to model a change in the direction of light when the corpuscles bounced off some surface, that is, reflection, or when they travelled from one medium into another of different optical density, that is, refraction. However, if this ballistic corpuscular ray model of the conveyance of light was accurate, then a parallel beam of light travelling through a crisp-edged aperture in a single medium should cast a strict, crisp shadow of the aperture. The problem is that repeated detailed observations like those of Da Vinci and Grimaldi showed that this is not the case, but that the edges of the shadow are blurry with some undulating fringes of light and dark in what ought to be shadow region, and these fringes were later accurately modeled as wave interference effects. These two experimental observations, the spreading out into shadow and the interference fringes, were strong evidence that the conveyance of light is better modeled as a wave phenomenon rather than ballistic objects traveling along straight ray trajectories. So, how can we model this diffraction behavior mathematically to allow us to predict its effects? The first useful mathematical modeling of the propagation of light as a wave phenomenon is due to the 17th century Dutch scientist Christiaan Huygens, which he published in 1690 in his book about light. Although Huygens himself only used this to model reflection and refraction, his principle was later used by Fresnel and others to model diffraction. Consider a plane wavefront like this traveling towards an aperture. If we just use this simple single wave model, then when the wave travels through the aperture, you get this part of the wave on the other side with total absence of wave activity in the regions of shadow, as ray theory predicts. But we know from real-world observations that this is wrong. Huygens asserted that each point on a wavefront acts as a center of a secondary spherical wave disturbance called a wavelet, and that the shape of the wavefront at any distant position can then be given by the envelope of all the disturbances of all these secondary wavelets. So, in this example, if we consider the wavefronts to this point here, we can find out the shape of the wavefront at a further position, like here, by making each point on this wavefront send out a spherical wavelet, and then take the envelope of all those secondary wavelets at the new position, like this. I'm only drawing the wavelets from a few points on the originating wavefront for simplicity, but the Huygens theory states that every single point on the wavefront emits a wavelet. From a mathematical perspective, therefore, this would imply an infinite number of wavelets would arise from any finite length of originating wavefront. For a single plane wavefront traveling in an unobstructed way, the result of the Huygens construction is just identical to the simple single wave model. However, after a part of the wavefront gets blocked by an aperture, in the Huygens construction, the secondary wavelets near the obstruction are no longer reinforced by a continuous stream of wavelets on the other side of the blocking parts of the aperture. So, the envelope of the remaining wavefronts spreads out into the region of shadow to look more like the diffraction effects you see with real-world waves. Huygens' construction gives us a simple and visually intuitive qualitative way to understand diffraction effects, but without modification, it's not quantitative or totally correct. To try and get a mathematically quantitative formula that will allow us to calculate the amount and pattern of diffracted light, in about 1818, French physicist Augustin Jean Fresnel combined the Huygens construction with integration of the amplitudes of the secondary wavelets, taking into account interference effects as described by Thomas Young. However, Fresnel realized the Huygens construction per se was not quite accurate compared to real-world measurements of diffraction, because in the Huygens model, diffracted light in the shadow regions continues unattenuated all the way to the back surface of the aperture, and also there will be a wavelet envelope traveling backwards, regardless of whether there is an aperture present or not, and a back-propagating wave is not detected in real-world measurements of light and other wave phenomena. Fresnel fixed these limitations with two empirical ad hoc bolt-on corrections to the Huygens model. First, to accurately mimic the attenuation of diffracted light with angle of diffraction, Fresnel added a coefficient term to his equations for each wavelet, called an inclination factor or obliquity factor. This is simply a cosine term used as a coefficient to modify the amplitude of each secondary wavelet, where the angle in the term is the angle from the current direction of travel of the wavefront at the point where the secondary wavelet is generated. This makes the amplitude of the secondary wavelet gradually decrease with increasing angle of deviation from this direction. This inclination factor works quite well at modeling how real light is attenuated with angle of diffraction, but Fresnel did not derive it from some first principle, but rather it was his intuition, and, as it turned out, it just works, empirically. The other empirical fix Fresnel made was to arbitrarily set to zero all aspects of the secondary wavelets travelling backwards. Again, he provided no theory or mathematical derivation to justify this. It was added ad hoc, because it just worked. In making these empirical fixes, Fresnel caused Huygens' construction to be a basis for a quantitative mathematical modelling of diffraction effects. Hence you'll sometimes hear this called the Huygens-Fresnel principle, and the resulting formulae are known as the normalized Fresnel integrals. I'll put links in the video description if you want to learn more about the maths in detail. Later, in 1882, Gustav Robert Kirchhoff used detailed integration of the wave equation, derived from Maxwell's equations, to calculate the effects of light at any distance from a source. He did include a forum of Huygens' ideas to help with this, but there was a lot of additional differential equation maths involved, like Gauss's divergence theorem, and I'll leave a link in the video description again for those who want to explore those maths in more detail. Kirchhoff's wave equation approach proved to be a practically accurate way of mathematically modelling diffraction based on the physics of EM waves, and without the ad hoc maths of Fresnel. However, this came at the expense of losing obvious direct connection with the intuitive and appealingly simple geometrical model of Huygens. The Fresnel and Kirchhoff equations continued to be standard methods for modelling diffraction to this day, and the original Huygens model, despite its easy-to-understand visual appeal, is recognized as being insufficient to describe diffraction in detail because of the shortcomings identified by Fresnel. That is, until about 300 years after Huygens, in 1991, while working at Bell Labs in New Jersey, physicist and electrical engineer David Andrew Barclay Miller published a paper in which he showed how, using a relatively minor tweak, the original Huygens construction can be used to give a mathematical model of diffraction that was just as good as the rigorous Kirchhoff wave equation formulae, while retaining Huygens' geometrical intuitive simplicity. Miller's tweak involved changing the structure of the secondary wavelets from monopole emitter waves, which is what Huygens, Young, Fresnel and those who came after them all assumed, to dipole emitter waves. As you can see from these animations, the monopole wavelet has all the problems that Fresnel tried to fix with his ad hoc solutions. The amplitude is the same at all angles, which Fresnel fixed with his bolt-on obliquity factor, and the phase of the wave is the same in all directions, including backwards, which Fresnel and Huygens simply ignored. In contrast, the dipole wavelet flips its phase between forwards and backwards propagation direction. This has the effect that it naturally attenuates its amplitude with increasing angle away from the forward direction, so there is no need for an obliquity factor. And, as for the problem of back propagation, it can be shown that the reversal of phase of the dipole causes all back propagation amplitude to simply cancel out once continuous integration of all secondary wavelets along the whole primary wave is done. Thus, applying simple integration of a dipole-based Huygens construction results in an accurate quantitative model of diffraction without the need for the bolt-on fixes of Fresnel or the complicated mathematics of Kirchhoff. Others have since sought to make Huygens work with different tweaks, but to my mind at least, the Miller dipole solution seems the most simple and geometrically intuitive, so that's the method I use in my software to simulate wave optics. To help with my teaching and research, I wrote a program to implement this Huygens-Miller model in the C programming language. If you want to play with it, you can download the program called HMS as part of my free and open source Biochem Image Processing Suite, or BIPS, and I made a separate video on that software if you need some help getting started with it. Be sure you have the latest version of HMS, currently version 1.1, because the original version 1.0 had several bugs that have since been fixed and was harder to use. The HMS program also simulates the slowing down of the group velocity of waves in areas where the medium is not a vacuum, that is, in areas with a refractive index greater than 1. This means that HMS can simulate refraction as well as diffraction. However, HMS was designed primarily for demonstrating basic principles and not for designing complex practical optical systems. So if that's your goal, you probably should use one of the many other optics design software packages available instead. Also, calculating a full Huygens-Miller model, which requires integration of an infinite number of wavelets, is impractical. So I had to cut some corners and limit the resolution of the simulation. In addition to making the calculations practical, this had two main effects. The first is that the full benefit of the cancellation of backpropagating waves by the Millerian dipoles is not achieved. Only a partial cancellation is seen, but this is good enough for demo purposes. The second and unexpected effect was that making these shortcuts actually improved the performance of the model using simple monopole wavelets as per the original Huygens model. As these are much faster to calculate, I therefore include the option of using either monopoles or dipoles in a simulation. Finally, HMS only does the simulation in 2D. For all these reasons, the HMS results will never be exactly the same as a 2D sample through a 3D light field, but the results are close enough for teaching purposes. If you've only learnt basic ray or corpuscular ballistic optics, you might be forgiven for thinking that the bright focal spot of light you see on the other side of an illuminated convex lens is due to all the little balls of light that supposedly make up the rays being diverted by the shape of the glass to meet at one point, and so concentrate there, as shown in this ray optics simulation. This ray model predicts the focused spot will be a nice, clean, crisp-edged single point of light at the center of a concentrating and fading double cone. And that's all, assuming the lens is the correct shape and free of aberrations. It predicts that the energy which gives rise to light will be absent in all places outside this double cone. If there are lens aberrations, then maybe the double cone of light will be smeared out of shape or asymmetrical, but otherwise it will still be a relatively simple region of light with the absence of photonic energy outside its boundaries. However, even with the most highly corrected precision optics, we don't actually see a single blob of light at the center of a simple double cone, let alone a crisp-edged one. Instead, we see a distribution of light that looks more like one of these, which are actual practical experiment recorded light distributions from this 2017 publication by Lambert and Waters in the Journal of Cell Biology. The asymmetries of the cones are due to spherical aberrations, but even if the aberrations are highly corrected, you'll always get these wave-like undulations fading away from a central blurry-edged focused spot, with surrounding rings of light in what ray optics predicts will be regions of darkness outside the cones. Here, as seen in these 2D cross-section views, those rings are represented by these thorn-like structures coming out of the cones. In all such experiments, if you look carefully enough, you will never see a simple double cone as predicted by ray theory. So what does the Huygens-Miller wave simulation of a focused spot of light look like? To find out, I constructed this refractive index medium image to use as input to the HMS program. Here, everything to the left is considered vacuum, with a refractive index of 1, and everything in this area will have the refractive index of glass being 1.518. To keep the optical transitions to a minimum, I'll be focusing the light inside the glass of the lens, so this is equivalent to the situation with oil immersion microscopy, or even to what is happening in your eyeball, if this is the combined cornea and ocular lens area, and this is the vitreous humor with your retina over here somewhere. The initial wave input will be on the left and will be a plane wavefront, which is the equivalent of a parallel beam, with a high degree of spatial coherence. I'll then run the HMS program to evolve the waveform as it progresses from left to right into the glass, using Millerian dipole secondary wavelets in the Huygens construction. And here is the result, shown as EM waves in the animation on the top to make it clear as to what's going on, and on the bottom here I show the intensity plot, which is what we would see if we put a projection screen at any and every point along the path of this wave field. Clearly, the focused light by this Huygens-Miller wave simulation resembles much more closely the actual observed optical measurement, with these wave-like undulations in the cones and these thorns representing side lobe rings around the focused spot, rather than the simple ray optics model. The precise shape of the light distribution in this simulation is not exactly the same as with the optical measurements, but that's just because of the limitations of the simulation I discussed in the previous section, and the geometry of the simple lens I'm using in this simulation will not be the same as the multi-lens compound microscope objective used in the practical measurement experiments. But the result of the simulation is clearly of the same type as what we see in real-world observations. So what is going on? How do spatially infinite waves result in a spatially localized focus of intensity, and what do I mean by that? Well, first of all, I say spatially infinite waves because the pattern you see here is produced by the superposition of a multitude of secondary Huygens-Miller dipole wavelets, and each of those wavelets just carries on expanding and waving forever across every part of the simulation and beyond, even in the regions of darkness. The reason you don't see wavelets in the dark regions in this case is that the curved interface between vacuum and glass causes each of the adjacent wavelets just beyond the interface to have a slightly different phase relative to each other. That phase difference is such as to cause their wave disturbances to interfere with each other in such a way that they cancel each other out in most regions of space, and especially in the regions of darkness, but reinforce each other in the conical regions of light, and maximally reinforce at the focus region. You can see what's happening in this sequence of simulations. Here I model the situation where the surface of the lens is covered in opaque paint, and at a various number of points I pierce the paint with a little pinhole to allow only one wavelet through at those pinhole points. So in this case we have just one pinhole only allowing a single dipole wavelet through into the glass, and you can see the waves of the wavelet filling the whole space, even those areas that eventually will be dark. In this simulation I've added another pinhole down here, so now two wavelets get through into the glass and their waves combine to form an interference pattern, with some regions that have destructive interference and others with reinforcing interference. The result is a patchwork of light and dark intensity fringes. As I gradually add more pinholes, the destructive interference areas gradually coalesce into pools of darkness, here outside the cone-like regions of mostly constructive interference. And, eventually, as more pinholes are added, those pools of destructive interference get bigger and coalesce, till eventually they form the regions of darkness outside the cones of light, and you can see that all the wavelets tend to reinforce each other in the focal spot, which is actually an elongated region, and not a very tight spot in the depth dimension. It is the length of this elongated central brightest region that determines the depth of focus of the lens. Now, recall from my second photology video that interference between any two waves does not actually alter the waves themselves. So, if they could get past each other, they would carry on waving as normal forever, or until they interact with something that alters the energy in the wave. Furthermore, each individual wave continues to wave as normal even in the zone of overlap with other waves, the zone of interference. If you think about it, this must be the case, otherwise the interference pattern could not exist. This holds true just as much for regions of destructive interference or darkness, as well as for regions of constructive interference. This means, as you can see here, that the wavelets of light continue to exist as normal in the areas that appear completely dark. In fact, they must exist here in a destructive phase relation to each other in order for this region to be dark. So what I'm saying is that there are two types of darkness. Darkness that is due to the absence of EM radiation, and darkness which is produced by EM radiation. In these regions here, the darkness is made out of light. If you could find a way to separate or isolate the wavelets in these dark regions, or selectively alter their phase relationships, you would cause light to shine out of darkness. You might want to pause the video at this stage and think about that for a moment. Thus, the focused wavy bright spot of a lens is a form of spatially localized constructive interference of the spatially extended continuous wave fields of all the wavelets. What's going on here in space is analogous to the way continuous wave laser beams of slightly different frequencies can be interfered to produce extremely localized pulses of light in time, that is, femtosecond and picosecond laser light pulses. But I don't want to go into that in any detail here, other than to point to this as an analogy of making localized resultant wave features by means of interference between very extended wave components. So, in regards to focusing light by a refractive dioptric lens, that wavy localized focused spot we actually see in real-world optics can't be modeled by considering light to be rays of converging billiard ball-like corpuscles. But it can be modeled, and very well modeled, as a localized region of constructive interference of an infinite number of infinitely extensive dipole wavelets that show mostly destructive interference everywhere else. If you like this video, please hit the thumbs up like button and view some of the other videos on my channel. If you'd like to support the project, you can do that by subscribing to this channel and telling others about it. If you'd like to help me continue this work, take a look at my Patreon page, where you'll find additional content and early bird access to future videos. Thanks for watching.